Hello everyone, I'm Tomonori Murakawa and I'm a graduate course student in the Civil Engineering Department of Osaka Institute of Technology in Japan. Today I'm going to present my research on the mechanical properties and resistance coefficient of carbon steel during fire. This is a follow of our presentation. So now we'd like to share a bit of background of our research with you. In recent years, bridge fires have been caused by various factors such as accidental fire during constructions and vehicle accidents in Japan and abroad. Major examples of bridge fires summarized in this table. This slide shows one example of bridge fire from the previous table. This bridge fire case was caused by an accidental overturning of a tank lorry. As a result of the bridge fire, the height of the steel gutter sank from 1,200 mm to 700 mm due to shear buckling at the region of the support. Consequently, this urban expressway was closed for about 2.5 months due to repair works. The point is, bridge fires have a great impact on society. When a bridge fire occurs, in the worst case, the bridge falls down, and it greatly affects the societies. In order to avoid such situations, it is necessary to grasp the effect of the strength rolling of steel in the fire on the structural characteristics of steel bridges, and to clarify the collapse mechanism. And it is necessary to carry out the fire resistance design many of the bridges of the main tracks road. Therefore, it is necessary to grasp the mechanical properties of steel at high temperature. In Japan, there are existing studies up to 900 degrees as shown in this figure on the right. However, in recent years, bridge fires exceeding 1,000 degrees have been reported. Therefore, it is necessary to understand the relationship between strength and temperature above 1,000 degrees. In addition, the design method for bridges in Japan have changed in recent years, but they don't consider the design method for the safety of bridges after fire. Therefore, reliability incidents, load factors, and resistance coefficients will studied with the aim for clarifying the resistance coefficients under fire conditions. However, in these studies, the partial coefficients for fire have not been considered. The current problem of bridge fire are as shown in the previous slide. In order to solve these problems, high temperature tensile tests were carried out in order to clarify the mechanical properties of carbon steel at temperatures above 1,000 degrees. Based on the result, the partial confidence were obtained by referring to the load and resistance factor design method of a chute. From this slide, we will discuss high temperature tensile testing. The tests were carried out using universal testing machines as shown in this photo on the right. The test specimens we mainly of steel gutter applied for the bridges. The dimensions that test piece are shown in this figure. The mechanical properties of each steel gut are shown in this table. The test conditions were summarized in these tables. The heating control positions was set at the center of the specimens. In addition, the heating speed was 20 degrees per minute, and the soaking time was 30 minutes. Furthermore, the tensile speed was determined in accordance with GIS 0567. This slide shows the result of high-temperature tensile tests. First of all, the SM400. SM400 means the minimum tensile strength of carbon steel is 400 Newton per square millimeter. The relationship between load and displacement shows that the load decreases as the temperature increases. As can be seen for this figure, there is a tendency for the carbon steel to fracture at 200 degrees, which is called blue heat embodiment. Now let's look at the other steel types. This slide shows the result for the other steel types. The result of these tests all show the same graphical trend to that of the SM400. Next slide, we will discuss the 1% and 2% proof stress. The result shows that for all types of carbon steel, the downward trend is almost identical to the result of exchanging studies. Finally, the reduction of the elastic modulus and tensile strength is described. For these figures, we find the same decreasing trend as in previous studies. From this slide, we will discuss the considerations of partial coefficients. The LRFD method defined by Ashut is shown in these equations of the left. The partial coefficients are calculated by converting the live load to temperature load, because the bridge is not subject to live load during fire. Also, the partial factor with reliability index in the ultimate limit state in the lower part of table were estimated in this study. First, the result of calculations of the resistance factor at 1% proof stress are shown. This figure shows that in the case of each carbon steel types at 200 degrees and 500 degrees, the resistance force of the member was from 90% to 99% of the total plastic axial force at each temperature. In the case of 800 degrees and 1100 degrees, the resistance force the member shown at wide range of from 85% to 99% of the total plastic axial force at each temperature. Next, the result of calculations of the resistance factor at 2% proof stress are shown. As can be seen, the result shows the same trend as for the 1% proof stress. I'm about to wrap up my presentation. We carried out experiment to clarify the mechanical properties of carbon steel at high temperature. From that result, what coefficient of resistance was discussed. The conclusion obtained from these studies are summarized as this. First, the carbon steel was found that the strength decreased with increasing temperature at all times. Next, the values of the resistance coefficients at 800 degrees and 1100 resulted in a lower assessment of the resistance of component than those at 200 degrees and 500 degrees. This is all for my presentation. Thank you for your kind attention.